Hi everyone and welcome. Today we're diving into the fascinating world of C programming. Now, some of you might be thinking, C, isn't that a bit old-fashioned? And you know what? You're not entirely wrong. C has been around for decades, developed by the brilliant Dennis Ritchie back in the early 1970s. But here's the thing about C. It's like the bedrock of modern computing. Think of it as the foundation upon which countless other languages like C++, Java, and even Python were built. These languages, as powerful and versatile as they are, owe a great debt to C. Why? Because C is all about efficiency, speed, and getting you as close to the metal as possible. It gives you incredible control over system resources, making it ideal for everything from operating systems to high-performance applications. So if you're ready to understand the DNA of modern programming, let's unpack this powerful language. One of the things that makes C so incredibly efficient is its direct access to memory. You see, when you write a C program, you're working very closely with the computer's hardware. You can allocate and manage memory with a level of control that's simply unmatched in many other languages. This low-level access translates to lightning-fast execution speeds. There's very little overhead, no bulky runtime environments to slow things down. It's just you, your code, and the bare metal of the machine. This is why C is often the language of choice for performance-critical applications. Think about things like operating systems, embedded systems, game engines, situations where every millisecond counts. C's efficiency and speed make it the perfect tool for the job. Now you might be thinking, okay, but what about portability? If C is so close to the hardware, won't I have to rewrite my programs for every different computer? And that's a great question. One of C's great strengths is its portability. The beauty of C is that while it gives you low-level access, it also provides a standardized way to interact with different hardware architectures. This means that with minimal tweaking, you can often compile and run your C code on various machines, whether it's a Windows PC, a Mac, a Linux server, or even an embedded system. C code has this remarkable ability to adapt and run smoothly. This write once, run anywhere philosophy has made C a favorite for projects where code needs to be deployed across a wide range of devices. So how does C achieve these blazing fast execution speeds? Part of the magic lies in the way C code is translated into instructions that computers can understand. You see, when you write a program in C, you're writing in a high-level language, something that's relatively easy for humans to read and understand. But computers don't speak C directly. They speak in the language of binary code ones and zeros. That's where compilation comes in. A C compiler acts as a translator, taking your human-readable code and converting it into those machine-level instructions. This compiled code is highly optimized, meaning it's stripped down to the bare essentials that the computer needs to execute your instructions. And because it talks directly to the hardware without the need for bulky interpreters or virtual machines, C programs run with incredible speed and efficiency. As your programs grow larger and more complex, C provides this wonderful concept of modularity. It's like having a well-organized toolbox where every tool has a specific purpose. In C, these tools are called functions. A function is a self-contained block of code designed to perform a specific task. For instance, you could have a function to calculate the area of a circle, another to sort a list of numbers, and so on. The beauty of functions is that they can be reused throughout your program. This modular approach not only makes your code cleaner and easier to manage, but also encourages reusability. You can build a library of functions for common tasks, saving yourself time and effort in the long run. This is one of the hallmarks of good C programming, breaking down complex problems into smaller, more manageable modules. Now, you don't have to reinvent the wheel every time you write a C program. C comes with this incredibly rich and powerful standard library that's packed with pre-built functions for all sorts of common tasks. Need to read or write data to a file? There's a function for that. How about performing complex mathematical calculations? C's got you covered. From input-output operations to string manipulation, memory management, and much more, the standard library is like having a Swiss Army knife of programming tools at your disposal. This means you can focus on the unique aspects of your program without having to write every single line of code from scratch. It's like having a team of expert programmers working behind the scenes, providing you with the building blocks you need to build robust and efficient applications. So, as we've seen, C, while being one of the oldest programming languages, is far from obsolete. Its efficiency, speed, portability, and the incredible control it gives you over system hardware make it relevant even today. If you're serious about understanding how software interacts with hardware, or if you're looking to dive into fields like operating systems, game development, or high-performance computing, learning C is an investment that will pay off for years to come. The basic structure of a C program is simple. You have your directives to import libraries, the function where your program execution begins, and within the function you write your code. For example, hash include int main, tabs into $10, b 20, sum =a plus b, print sum of %d and %d is %d, a, b, sum, return 0. This simple program adds two numbers and displays the result. But don't let its simplicity fool you. This is just the tip of the iceberg. As you delve deeper into C, you'll discover a world of possibilities, unlocking the ability to create sophisticated and powerful applications. So go ahead, explore the world of C and unlock your true programming potential.